We should go ahead and get started. Yeah, so thanks a lot for coming back. Our first talk of the afternoon is going to be Haipeng, who's going to talk to us about no regret learning in time varying zero-sum games. And then after that, we're going to have Eric talking as well. And just one quick reminder is, if you have open problems, add them to the sign up board for tomorrow. Should be a lot of fun. But with that, I think I'll hand it off to Haipeng.
Thank you. Thanks for the introduction. So I'm going to talk about no regret learning in time varying zero-sum games. So this is joint work with my student Mengxiao. We are from USC, and two collaborators from Nanjing University, Peng and Zhihua. Okay. So I guess for this audience, I don't need to convince you that uncoupled learning dynamics for a fixed game is well studied. Okay. So, but what we started to think about is what if the game is changing over time? Okay, so in some cases, these changes, they depend on the player's actions. In which case you can model this as either a Markov game, extensive form games, etc. Okay, so I will take an example from Eva Tado's talk earlier in this program. So she mentioned packet traffic routing over the internet. And so in this case, the game is changing over time. And that's because there are unserved packets from previous rounds. And that is determined, or at least partially determined by the player's actions. Okay? So that falls into this case. But I want to argue that there are also other cases where the changes they are only caused by some exogenous factors. Okay, that they are not determined by the player's actions. Okay? So if we look at this example, this morning rush hour traffic. So the game can change over time, but the changes, for example, they come from either the road construction or some accidents. Okay, so which has little to do with the player's actions. So in this talk, I'm going to focus on this second case. So the changes are caused by exogenous factors. It turns out that at least to our understanding is not very well studied, surprisingly. So in particular, I'm going to focus on uncoupled learning over a sequence of time varying two-player zero-sum normal form games. Okay, again, they are changing exogenously by the environment. So, and I'm focusing on the simplest case, the normal form games, so no RL in this talk, although I will come back to this as a future direction in the end. Okay? But even for this simplest case, it turns out that how to measure the performance requires some careful thought. Okay, so that's going to be the first part of this talk. So I'm going to, in particular, I'm going to review existing measure. I'm going to argue why it is problematic, at least for some cases. And then I'm going to consider three natural measures. One of them is new, it's proposed by us. Then in the second part of the talk, I'm going to move on to propose one algorithm that we designed. And this is a parameter-free algorithm. And it achieves strong guarantees under all the three performance measures that we consider, okay, simultaneously. And importantly, it also kind of recovers the best known results when the game is fixed. Okay, so that's kind of the agenda for my talk. So let me now go into the setup. So again, we're considering this a repeated game setting, where for each round T of the game, the environment first decides a payoff matrix AT. Okay, so let's say the payoffs are all normalized between -1 to 1, and AT depends on T, so it's changing over time. So without knowing the payoff matrix AT, X player decides a mixed strategy XT from the simplex over M actions. Okay, and simultaneously, Y player decides a mixed strategy YT from the simplex over N actions. Okay. So, and then X player suffers loss XT transpose ATYT, okay, which is standard, and observed this loss vector ATYT And so in other words, he can reason about like what he would have suffered if he chose a different mixed strategy. Okay. And similarly, a Y player receive the same value, but as the reward, and see this vector xt transpose at. Okay, so this is sometimes called a mixture feedback, and it's also kind of well studied when at is fixed. Okay, so again, when at is fixed, this is this very standard repeated game learning setting. So, and I hope I convinced you that there are cases where at is indeed changing over time, and it's decided like exogenously by the environment. And if you're not convinced yet, there are also kind of more kind of implicit or theoretical applications of this model. For example, these two problems, online LP and adversarial bandits with knapsacks, they can all be modeled exactly as this problem. Okay? But I'm not going to go into the details. I hope the setup is clear. Right? So I'm going to mention a few related work. So the most related one is this one by Cardoso, Abernathy, Wang, and Xu. So they basically consider the exact same problem, except that their feedback is either the entire matrix 80, which is stronger than us, or just one entry sampled from the mixed strategy, okay, which is weaker than us. Okay. So I will come back to this work later. So another recent work is by Roy et al. So they consider the more general convex and concave games, but their performance measure is different, which I will also touch upon briefly later. And there are also other works, Duality et al. And also Fees et al. So they are less related. They do not exactly capture this problem that I'm considering. Okay, and I'm sure there are more that I'm not listing here. So okay, now let me tell you how. Let's discuss how to measure performance in this setting. So the most natural thing is still just to minimize the classical regret. So whether the game is changing or not, you can still always define and try to minimize the individual regret. Okay, so which makes sense for each player because they're just kind of selfishly minimizing the difference between their loss and the loss of the best fixed action in hindsight. Okay. Or best fixed strategy in hindsight. Okay, so that's the regret for X player. And again, it's the classical measure. And similarly for Y player, you can define the same thing. Okay. So you can still do that in time varying game. But beyond this individual regret, so we want to know what kind of other game theoretic guarantees we can argue about. So for example, when the game is fixed, it's well known that we can argue about the closeness of either the empirical strategy or even the last iterate to the last equilibrium of this fixed game A. Okay, so that's again well studied. And that's what I mean by game theoretic guarantees. And so now the question is, when AT is changing over time, then obviously you don't have a fixed set of Nash. And then what kind of similar guarantees you can argue about? Okay. So that's the question. And so one proposal here is something called a Nash equilibrium regret proposed by Cardoso et al. So they consider the difference between the actual value received by the players and the minimax value of the cumulative games, okay, the sum of AT. Okay, and they propose an algorithm that always guarantees sublinear bound on this any regret. Okay, so this looks reasonable at first glance. I'm going to argue that it has like two important issues. So the first issue is that it's actually incompatible with the classical regret that I talked about at the beginning. Okay, so this is actually already proven in their work. They show that no algorithm can achieve a sublinear bounds for both the classical regret and any regret simultaneously. So in other words, if you want to always have sublinear regret on this any regret, then there exists a sequence of games such that your individual regret is linear, which is vacuous. Okay, so that's what I mean by any regret is incompatible with classical regret. And that's kind of bad because, again, I think it's very natural to try to, for each player to try to kind of selfishly minimize a classical regret. Okay, so that's the first issue. And then the second issue is that we show that this any regret can in fact be linear in T, even for perfect players. So here by perfect players, I mean players that always play the Nash in each round. Okay. So to see this, just consider a very simple example. Let's say for the first half of the rounds, you're just playing this game, which is just matching pennies. And then for the rest, you play this kind of boring game. So it's just two different games. And so it's easy to say that, to see that, so let's say we consider two players always play the Nash each time. Then for the first half of the rounds, then the value is just 0. Okay? Everything is symmetric here, so the value is 0. And for the second half, the value is going to be 1 because in the Nash, the white player is going to always pick the first column. Okay? And then no matter what the X player plays, the reward, the loss is 1. So that's why the cumulative value, this part is T over 2. Okay. And if you look at the cumulative game, which is this, okay, it's easy to see that the value is just 0. Okay, X players always pick the second row. Okay, so this part is just 0. Okay, so in the end, the any regret for this perfect player turns out to be a linear in T. Okay, so that's why we think this measure is problematic in this sense. Is that clear? Okay, good. So kind of inspired by this issue, we propose a new measure that's similar. Yeah, go ahead. Yeah.
Actually, to consider metrics of different time very important.
Yes, that's exactly what I'm gonna talk about. Getting there. So yes, right. So in the first line, I'm listing the any request from this work, and what we propose is to kind of move the min-max inside the sum. Okay, so it means that we are comparing the value at each time and the min-max value of the game for that round. Okay, and we're looking at this cumulative difference. Okay.
Yeah, so another question I'd like to ask is, yeah, it's somehow obvious from the example that you need a dynamic Nash equilibrium regret, but do we have a budget about how much the games can change?
Yes, that's a very good question. Yes, in the end, we're going to measure the difficulty in terms of the kind of the non-stationarity of the game matrix. And I will talk about this very soon. Okay. All right. Okay. So again, dynamic any request what we propose, and so the connection between these any request and dynamic request is kind of just at least on the surface analogous to the connection between classical regret and its dynamic version. Okay. So this is the classical regret where you compete with the fixed action in hindsight. And the well-known dynamic version of this is just to move the min inside. Okay, so you're competing with the best sequence of actions. Okay, the best action at each time. Okay, this is also well studied. And again, our connection between these two is similar to this. Okay, yes.
So the dynamical one seems like strictly harder than the standard regret.
Yes.
For the classical setting.
Yes.
But in this game setting, it seems not necessarily the case.
Exactly. That's actually my next point.
Oh.
So for classical regret, always more than dynamic regret, but that's not true for the any regret. So dynamic any regret could be smaller than any regret. Okay. So to see this, just consider the perfect players again. So if they always play the Nash, then dynamic request obviously just 0. Okay, While in the example I showed you in the last line, you see that any regret is linear in this line, in this case. Okay. So that's why they're kind of analogous only on the surface. And more importantly, a dynamic regret is also compatible with classical regret, as we will see. So in other words, you can obtain meaningful guarantees for both of them simultaneously. Okay, that's why to us it makes more sense to consider dynamic any regret other than any regret.
So what you're saying is that what if any regret, they can also have some no regret, like squirrel to.
Yes.
But you're just considering some different regret.
Yes. Okay, good. All right, so the last thing I want to talk about in terms of measure is, so approaching the minimax value of the game doesn't really mean you're close, like at least in the traditional sense of being close to the Nash equilibrium. So instead, if you really want to measure the closeness to the Nash, you can look at, let's say, the duality gap. Okay, so this part is just the duality gap of the strategy XT and YT to the game with respect to game AT. Okay, and I'm just summing up all these duality gaps. Yes.
Still kind of the previous definition you had is a global one over all iterations, and besides natural some natural situations are not like that. You don't want to look at the global thing.
Right.
These kind of situations which.
Right, so that's more like adaptive regret in the online learning case.
Because usually maybe it changes slowly, or maybe the graph changes.
Right.
Right.
But in that case, our guarantee will be good also, right? If the change is small, the amount of changes is small, then you will get a favorable guarantees for these dynamic.
I don't see it immediately. Like, let's say the matrix changes 10 times.
Yes.
Like, then what will happen? Can you say what will happen?
Yeah, we will get a constant for this dynamic, and we can get constant for dynamic and
And slowly changing, you have something that depends.
yes, exactly. That's what I will get into. So, right. Okay, so duality gap is another natural one, and I mean, so there are of course other possibilities. You can also consider, let's say, let's say the R1 distance between XTYD to the set of Nash equilibrium. So you can also do that, and that's exactly what this paper by Roy et al. Does. But in this case, the bound usually depends on some problem-specific constant other than the size of the matrix. Okay, which is less appealing to us, so that's why we are not considering that in this work. Okay. So just to quickly summarize, we are considering these three measures in this work: the individual regret, the classical one, dynamic any regret, which is what we proposed, and also the natural duality gap. Okay. And a quick remark is that you can in fact show that the first two is always bounded by the last one. So duality gap is always the largest one, but this upper bound can be quite loose. So it doesn't mean that you just need to care about duality gap, because you can in some cases get much better bounds on the first two measures. Okay. And now let me get to this notion of non-stationarity that several of you have already mentioned. So it's very easy to see that no meaningful guarantees can be obtained for the last two measures if the game just changes arbitrarily. Okay, so you need some notion of to capture the difficulty of the problem. So in other words, you need some notion of non-stationarity of the payoff sequences. And so here we consider three. So the first two are the kind of the variation of this AT sequence, and also kind of the variance of the sequence. So A bar is the average of the games. Okay. And another one is you can also measure the variation in terms of the Nash. Okay. So this is the variation of the sequence of Nash. And let's say if you have multiple Nash, just consider the sequence that minimizes this quantity. Okay. So these are three kind of non-stationarity measure we consider. So in the worst case, they can all be like of order T, but they could be as long as it's not in the worst case, you can hope to get something good. And just again a quick remark: VT is kind of always bounded by WT up to some constant, but they are incompatible with PT generally. So you can come up with example where one is constant, the other is linear, and vice versa. Okay. And finally, let me just say again that the goal now is that whenever you are not in the worst case, so whenever these non-stationarity measures, or at least some of them, are sublinear in T, you hope to obtain sublinear bounds for, let's say, dynamic regret and the duality gap. So that's kind of the goal. All right. So if that's clear, let me go to the second part on our algorithm and guarantees. So again, we propose one parameter-free algorithm that obtains the following guarantees simultaneously. So when deployed by both players. Okay. So for individual regret, we obtain something like a square root of Qt, where Qt is kind of like this. So the variation of the game plus the minimum of the variation of the Nash and the variance of the game. Okay. So the important thing is that it's always bounded by root T, because Qt can at most be T. And in particular, when if the game turns out to be fixed, then Qt is just 0, and you get just O2 to 1 regret. So I'm hiding some log T factors here. And this recovers the best result by Scherzo. And similarly, for dynamic regret, you get something, again, in terms of all the non-stationarity measure. So it's going to be sublinear as long as one of PT or WT is sublinear. Okay. And again, when you are in the fixed game scenario, you get O2 to 1. Okay, so again, it recovers this work. And finally, for duality gap, because something even more complicated, but again, it's sublinear as long as Qt is sublinear. And when the game is fixed, you get root T, which recovers the best result from work for my group last year. And yeah, so that's it. That's kind of our result. And so as a lot mentioned, the last column actually also holds when, let's say, AT changes constant times. Okay, so because in this case, all these measures, they are just constant. I mean, except WT. Okay, but if you plug in the result, you can see that indeed you can get all these bounds, even if the game changes for constant times. Okay. And the last remark is that the individual regret, you can also have some robustness guarantee. So if only X player uses our algorithm and Y player kind of deviates from this algorithm, so let's say Y player behaves arbitrarily, you can still get root T regret for the X player. Yes?
So yeah, I agree that you get this all one thing, but the comparator is the min max, which can be worse than just the best strategy in hindsight for that particular fixed matrix.
But it's min max for each round.
Right, but let's say you have a bunch of rounds with the same matrix, right?
Yes.
So the min max is not as good as just the best strategy for whatever the adversary is doing, because he might have played suboptimal.
Not sure I understand, but again, the min max is for each round we are competing with the min max of that round.
Let's say there is no change in the matrix, then it doesn't matter one round or many rounds, right?
Okay.
But min max is not as good as just standard regret for a fixed matrix.
Yes, right.
But that's my point, right? So then it's not as good in that sense as compared to
I see what you mean. Yes. I mean, but in fact, I think we can also get like interval regret, although we are not actually showing that in this work.
Well, you will need to use a different, I don't know your technique, but you need to use some kind of shifting of space technique.
Yes, Yes, I mean, in the end, our algorithm, yes, it has some adaptive regression. Okay. Yes.
Is there any sense about optimality of that kind of results? It's like it's a PN dependence.
Yeah, that's a very good question. No, we don't have that. I mean, like we don't have like for each value of PT, VT, and WT, which is the law, we don't have that kind of law. And we also suspect, especially for duality gap, is not tight because if you can see that the exponent here do not add up to 1. So.
But you're saying like this VT and WT are comparable, but PT are not comparable. So
yes.
Do you have a result that says like both PT and WT or VT are necessary in this?
That's a good question. No, we haven't thought about that. That's a good question. Okay. So let me talk about a little bit about the algorithm design. So first, let's review what happened in the fixed game setting. So for fixed game, so in this work, Theoretic et al., we proposed this like RVU property that says that if your regret can be bounded by, let's say, the variation in the utility vectors, so AYT, or it's basically the negative utility for X player. And this is just the variation in the utility for X player. So you want your regret to be bounded by this quantity. And also what the name doesn't suggest is, but it's as important is this negative term in terms of the variation of this the strategy of X player. Okay, if you have an algorithm that satisfies this, we call it satisfying the RVU property. And here eta is a learning rate of the parameter of the algorithm, and alpha, beta, gamma, they're just some constant that you don't need to care about. Okay, so first, this is satisfied by many so-called optimistic online learning algorithms, such as optimistic hatch and optimistic gradient descent that I'm not going to talk about in details. But this RVU is useful because if you look at the blue term, the variation is actually bounded by the variation of the Y player strategy. Okay, and then if you compare these two red terms, they are basically symmetric. So meaning that if you, for example, sum up these the regret of X player and Y player, they basically cancel. Okay, so you don't have this second and third term anymore. So your regret is going to be very small. So and it has a lot of nice implication then. Okay, so that's what happened for a fixed game. And then for time varying games, which is our setting, it turns out that it's important to, again, consider competing with a sequence of time varying strategy. Let's go U1, U2 up to UT. And then we very naturally, we propose this dynamic RVU property. It says that we want our regret competing with this UT sequence to be bounded by basically the same thing, except AT is now changing. And also the first term 1 over eta now depends on this PTU, which is the variation of the comparator sequence U. Okay. So it's a very natural generalization. And importantly, it's also satisfied by standard algorithm. So for example, it's satisfied directly by optimistic gradient descent, which is written here. So don't worry about it if you don't know what it is. And it also satisfied by optimistic hatch if you do it over a truncated simplex. Okay. So that's that. And the thing is that for each performance measure that we consider, this property, this DRVU property, in fact, implies some guarantees already. Okay, so it requires some non-trivial analysis, especially for the duality gap, but it's enough. Okay, so DRVU is enough. But the thing is that the catch is that to do so, each measure requires a different tuning of the learning rate eta. Okay, and also the knowledge of the non-stationarity, the VT, WT, and PT. Okay, so that's why this is not enough. And to achieve all these guarantees simultaneously, and also without knowing the non-stationarity, what we propose is just to kind of maintain a set of base algorithms, each with this property, with some different tunings of eta. And then on top of this, we have another optimistic meta algorithm to learn over this set of base algorithms. Okay. This is, of course, also a standard idea. So this learning the learning rate framework is kind of standard. But the right execution here requires some new ideas, two new ideas in particular. And in terms of analysis, you also need to carefully control the overhead of the meta algorithm. Okay, how much more time do I have? Okay, okay. So let me just show you the algorithm overview. Then I guess I'm done then. So again, your input is just any base algorithm that satisfies the RVU, and I already give you two examples. Okay? So and then the meta algorithm maintains a set of log T base learners. So each satisfy the RVU property again with a certain eta from an exponential grid. Okay? So now at each time t, you first collect the strategy output by each base learner. Then you come up with some prediction vector MT that I'm not going to talk about. And then you update a distribution PT over the base learners, okay, according to this kind of gradient descent procedure, okay? Then your final action is just the mixture of the output of the base learner according to PT. Okay? So then you suffer the loss, you observe this vector, and you send it to each base learner so they can do their updates. And finally, you come up with some loss vector and update this kind of auxiliary sequence PT hat, okay, which is used in computing PT. Okay, so in other words, meta algorithm is in fact also just doing it's doing optimistic gradient descent, but over this space. Okay, the distribution over the base learners. Okay, but the two new ideas is first, it turns out that this is not enough. You also need a set of kind of dummy learner that always select a fixed action. Okay, so intuitively, this allows the meta algorithm to be directly comparable to the Nash at each time. Okay, you can find PT with these dummy learners. You can find PT so that this mixture is exactly the Nash. So that turns out to be important for the analysis. And second, in terms of how to design this MT and LT, it turns out that you need to add some bias towards more stable learners. Okay, you cannot just do the most natural thing. Okay, but I don't think I have time to go into this, so let me skip all these. Okay, we did some experiments. I'm not going to talk about that. So, okay, so to summarize, the takeaway is that for a sequence of time varying games, it actually requires more thought on how to measure the performance of a learning algorithm. Okay, so we provide some measures, but by no means they are the best. Okay, and so, but another thing is, another message is that simultaneously strong guarantees under different measures is possible. Okay, as we show in this work. And finally, let me conclude with some open questions. So the first one is kind of most related to this setup. So what the feedback model we have considered is this so-called full information mixture feedback, where you see this vector for X player. So of course you can consider that like the bandit version, or even the kind of the fully realization-based feedback. So which are much harder. And many techniques in this work actually fail, unfortunately. Okay, so we don't really know what to do. Second direction is to consider kind of general sum games. And finally, so recall that at the beginning I said the changes from time varying games can depend on either the player's action or by the environment. Okay, but in fact, you can also have changes coming from both. Okay, so that's kind of like, for example, you can model it as a time varying Markov games. Okay, which I don't think we know much about. Okay, so these are the three directions that I think are interesting. So that concludes my talk. Thanks.
Thanks a lot. Yeah, in the interest of time, why don't we maybe take like one question, and then maybe Haipeng can answer any other questions offline. Yeah, let me give you the mic.
Thank you. Yeah, thanks, Haipeng. This is very interesting. So when do you think it is a better idea to look at min-max as opposed to just regret? Like when do you think this can be a good idea? Like in a static game, I think regret kind of says it's not a good idea. So I wonder, like
No, I don't think it's a good idea to only look at one of these measures, but that's why we consider several measures simultaneously, right? We also have regret guarantee. We are not just competing with minimax values.
But for minimax, that's the main, I guess that's the main new thing, the minimax values.
But
Or-
again, well, that's one the main measure we propose. But again, in the end, I always achieve guarantees for several measures simultaneously, and that's the more difficult part.
Thanks a lot. Let's give Haipeng
Thanks.
another round of applause.